Good morning and good afternoon, everyone. My name is Brian Foster, Content Director here at PingCap, and I'll be your MC for today's event. Over the last few decades, organizations with data-intensive workloads have largely turned to SQL and NoSQL. However, while these databases solve the immediate problem of scale, they make major sacrifices in data integrity, hard-to-detect data corruption, application complexity, rigidity, and even resistance to data change. TiDB is an open source distributed SQL database that evolves this story in major ways. Its multi-writer architecture allows for scaling throughput linearly while maintaining strong ACID compliance. And by decoupling storage and compute, TiDB's compute layer is stateless and independently scalable. In today's webinar, we're delighted to have PingCap Senior Solutions Engineer Matthew Penaroza share the design goals and architecture of TiDB and how it leverages these to keep performance stable as it horizontally scales, not just in online traffic, but in schema changes as well. But before we get started, please feel free to drop your questions directly in the chat window. We'll be sure to answer them during the Q&A portion at the end of the talk. And before we get things kicked off here, we'd like to get started with a poll question. So what is your primary challenge with your current database setup? We'll leave this up for a few moments and get kicked off from there. All right. And with that, I'd like to hand it over to Matthew. Matthew, the floor is yours.
Cool. Thank you, Brian. Hello, everyone. Welcome to our October webinar. And today I'm going to be introducing you all to TiDB. And my name is Matthew Penaroza. Okay. So the agenda for today, if everyone's cool with it, first of all, I'm going to do a quick intro, introduce myself and my background. Then we're going to talk about the problem that has really been facing a lot of modern applications today, and that's the problem of rapid data growth. And then we're going to talk about a potential solution to these problems, which would be TiDB, the company I represent. And then we're going to talk about the results that a lot of companies had adopting TiDB in production. And then finally, we'll wrap it up with a Q&A where you can get all your questions answered, or as many as we can, at the very least. Okay, jumping in. My name is Matthew Penaroza, and I am a solution engineer here at PingCap. I am based in Austin, Texas, and it's my job to solution technical challenges, particularly architectural challenges, at scale for some of TiDB's largest customers in North America. My background is I was born and raised in Ewa Beach, Hawaii. I'm a former engineer in the finance and streaming sectors, and I was also a prominent streamer and competitive Dota 2 player. Fun fact. Okay, now we've introduced myself. Let's talk about the problem here. Rapid data growth. New applications or modern applications like finance applications, generative AI applications, social media applications are facing a problem that they've never really faced before, at least at this scale. And that is the problem of rapid data growth. The growth of data is faster than it's ever been before. And the growth of data also never stops. As data grows and grows and grows, you never get rid of that. That data is always valuable to your application, for historical analysis and things like that. And potential solutions to this problem and legacy solutions would be things like sharding. Sharding was one of the first solutions taken to address massive data growth. And then NoSQL came around. That also became a very prominent solution, but there were sacrifices with NoSQL. You no longer got the ACID transaction integrity that you got from typical SQL databases. There was also primary, secondary replication and read and write separations. And these are all potential fine solutions, but they all have individual downsides. And that's kind of where distributed SQL comes into play. So what is distributed SQL? Well, starting off, let's talk about how distributed SQL came to be in the first place. Databases started off as your single instance relational databases. And these databases enforce ACID transactions. They were full SQL, had full SQL support. They had guaranteed data integrity. But when you got to scale, it really introduced operational complexity into your system. And then NoSQL databases came around to solve these problems of these relational databases. And they introduced features that allowed for higher scalability, flexible schemas, higher reliability. But their downside is that they had limited query capabilities and often had bespoke query languages. This is where distributed SQL comes in. And this is the category that TiDB is a part of. And what this new category does is it combines the scalability and reliability of NoSQL databases with the same functionality of relational database management systems, while also having the ability to scale to potentially petabytes of data size. Without the architectural baggage of legacy systems. And in fact, the database benefits off of all the lessons that have been learned over the course of decades of other companies building databases. We took the mistakes and the lessons that they've learned, and we have used that information to create a overall better and scalable and more modern product in TiDB. We are also the most popular open source distributed database on GitHub. We have over 10,000 production adopters worldwide, over 800 contributors, and over 5,000 Slack users in our community. Now let's talk about TiDB's architecture here. One thing brilliant about TiDB is it essentially takes all of the individual processes of a typical relational database system, like let's say Postgres or MySQL, and it divides up those internal processes into different individual nodes. And number one, it does this for scalability, but it also does this for high availability. So you can guarantee that one of these individual processes has a failover node ready just in case of the event of a server outage. Starting with our TiKV nodes. Our TiKV nodes are a distributed storage layer. And these storage layers store your data, and they do auto and transparent data sharding to ensure that your data integrity is handled across different nodes. Then we have our stateless SQL layer. These are what we call our TiDB nodes. And these nodes are responsible for SQL processing as well as distributed computing. And every single one of these nodes can be scaled out or in a very short period of time. And they're all open for read and write. And then finally, we have our PD nodes. And the PD nodes are essentially the brain of the cluster. And they're responsible for data placement, data safety, workload balance, and data integrity through guaranteeing the timestamp of each individual transaction. Okay, now let's take a deeper look under the hood. So when you store data into TiDB, this data is auto-sharded, and that it's first mapped from the SQL format to the key value format. And this key value format of the data is actually hidden from you. So as far as you're concerned, when you're using the database, it'll present like it's a typical row-based storage engine. And it'll split this data into small chunks, which are 96 megabytes by default. And the advantage of this is that the database can then move around these individual chunks to, let's say, individual availability zones, different nodes. And each one of these regions, as we call it, has multiple replicas that act as a consensus group to guarantee that your data is consistent when it's stored. So one of these regions will act as the leader node, and these other regions will act as follower nodes. And through a election process of checking the data integrity of each one of these regions, you can guarantee that the leader region is actually has the most correct version of the data. Okay, now moving into transactions. So as I mentioned before, all transactions on TiDB have ACID guarantees. We also have snapshot isolation in our transactions, and every single TiDB node can take both reads and writes, and these TiDB nodes can be scaled out almost indefinitely. So you don't run into a single writer bottleneck like you might on Aurora when you're scaling out. And we also natively support distributed transactions, which are also transparent to the application and strongly consistent. We guarantee consistency between the individual nodes that take place in a distributed transaction through what we call two-phase commit. And what essentially is happening there is that our compute nodes will first do a pre-write check to the individual TiKB nodes where your data is stored, check to make sure that the data there is valid to be written. And then once that happens, it'll send a ping back to the TiDB node, letting it know that the data is ready to be written, and then it'll finally commit the changes to the TiKB nodes. And this way, we can actually maintain consistency throughout this entire distributed transaction process. And we also support a high-performance one-phase commit with asynchronous commit of the follower nodes in specific scenarios. We can also scale both reads and writes. Now, if your application looks like this, and then it looks like this, oftentimes this is a huge problem for databases. But with TiDB, if you need more QPS support per second, you can just add in a couple TiDB nodes seamlessly. Or if you need to store more data, you can add in a few more TiKB nodes. And the system will automatically balance this out, and while simultaneously present a single view of your data. It's not as if when you access a TiDB node, a specific TiDB node, or a specific TiDKB node, that you're accessing only a portion of your data. You actually have an insight into all of the data that exists across the cluster in a consistent manner. Now, reliability is critical and complex, as I'm sure all of you know. And reliability affects the quality of your user's experience, particularly if you're working at scale. So what do we need to plan for when we're factoring in reliability to the equation? Number one, server events, rack level outages, building zone level outages due to water or fire, major regional disasters like what's happening down in Florida, unfortunately, accidental data deletion or modification of the data, or even bugs in your application. And this is an end-to-end discipline that must be built in to the foundation of your application. It cannot be bolted on later as an afterthought.
All right.
So
Matthew, let's stop for a second. I think we're going to do it's time for a quick poll question. I think everyone just kind of a chance to just kind of take a quick breather, for you to have some water. So folks, how familiar are you or your team with the concept of distributed SQL? We'll leave this up for a few minutes, and then we'll get back to our scheduled programming. All righty. Back to you, Matthew.
All righty. Okay. Now, talking about high availability and disaster recovery, this needs to be built into your systems. And there are a number of different layers of reliability that are built in to TiDB. And some are optional and some are inherent to the system. So number one, we have backup and restore. You can do daily full backups with TiDB to rebuild the cluster to recover. Now, upside of this, it's very cheap. You only have to pay for a specific amount of storage. Downside here is your RTO and RPO is going to be potentially hours. Then we also have point-in-time recovery, which continuously back up your data over time. And with this, you can achieve an RPO of less than 5 minutes, but your recovery time objective is going to be hours if the cluster goes down. We also have flashback if you're restoring a cluster to a specific point in time that's within your garbage collection lifestyle or lifetime. And with that, you can achieve an RTO of minutes and an RPO of 0. And then we also have a primary secondary replication. And with this, you can actually achieve, and I know it says minutes, but potentially seconds of RTO and RPO by having a secondary cluster on standby that you can switch to when a disaster occurs. And then finally, we have Raft, which is inherent to the database system. And with this, you can achieve an RTO of seconds and an RPO of 0. And with Raft, you can automatically, it has automatic data replication and recovery with strong consistency and self-healing properties. Now, let's talk about online schema changes. With TiDB, you can do things that are potentially impossible or extremely difficult, or even take hours on traditional database systems. So with online DDB or DDL in TiDB, there is no downtime when you make changes to your schema. You can make changes while the database is running with almost no impact on your applications. Your queries can run normal with no effect on read and write latency and data consistency. Now, you probably ask yourself how. So the schema changes run as a background job and leverage multiple nodes to run single heavy DDL. And DDL tasks are persisted to TiKV and can restart after node reboot or failure. Now, let's jump into distributed computing. So let's say you have a query like this, where select count from star, select count from star from T, where ID is greater than 10 and C2 equals foo. In a traditional system, this would all be done on a single instance. But in TiDB will split up the individual processes of this query and send it to all the individual nodes that are involved in this transaction. And these individual nodes down here will take a portion of the query plan executed on the TiDB node or on these TiKV nodes, and then send it back to the TiDB node for a final aggregation. And in this way, you can take full advantage of all of the compute power in your cluster, not just the compute power on your compute nodes. And then in addition to, well, TiDB is primarily a transactional database. However, one thing that is really convenient, particularly for our SaaS clientele, is that we have a TiFlash node add-on. And this TiFlash node add-on stores data in a columnar storage format instead of a row storage format. And the benefit of this is that you can have a single cluster where you can run massive transactional workloads at scale, while also being able to run massive analytical transactions at scale without the need for a separate analytical database or another final replica of your data. Okay, now in summary, the advantages of TiDB are number one, and I think core to the product is horizontal scaling. The fact that we can provide seamless scaling with automatic sharding is probably one of our greatest strengths. And in fact, in the distributed database space, with as far as scale is concerned, there's probably only one other database that really matches us in the scale sector. 4 nines of availability with guaranteed auto failover and self-healing for continuous access to your data. If something goes wrong in the database, the database has a lot of mechanisms to automatically solve your problem without manual intervention. Mixed workloads. As I mentioned before, we can support transactional workloads, analytical workloads, and even AI workloads, all in a single cluster with a single view of your data. And it's strongly consistent. We maintain ACID transactions with strong data integrity checks and global compliance. And we're also fully MySQL compatible. And I know it's saying we're the world's most MySQL compatible distributed SQL database? I'm pretty sure that we're one of the only ones. So definitely, and our MySQL compatible for distributed databases is second to none. And we also support multi-cloud deployments, whether you want to deploy on your own data center, on Azure, AWS, GCP, wherever you go, we can go to. And we're 100% open source. We're not a BSL license. We are full Apache open source. And so you can take advantage of that through transparent innovation, community-driven community-driven changes, as well as a guaranteed and secure database because you can see the source code. And we also provide security and compliance. We support both in-flight and at-rest encryption. Now let's take a look at the results here and look at how TiDB functions in production. Now, TiDB is trusted by trailblazers in a lot of different spaces, particularly in the finance space with Square and Plaid. Plaid, which processes a huge percentage of the financial transactions on the internet. Conga and Catalyst, who are both in the SaaS space. Capcom in the gaming space, and Bolt in the rideshare space. They're actually like the Uber of Europe, if you're not familiar with them. And these guys all run on TiDB. We also have a number of awards where we were part of the Gartner Magic Quadrant. We were awarded the Peer Insights Customer Choice Award in 2024. We were a Wave Strong Performer Award by Forrester, and a bunch of other different awards, and we're very prominent yet. Okay, now let's talk about the top TiDB use cases. I would say these are our core use cases which customers come to us for. Number one, scaling single node relational database systems. If you are on Aurora, if you're on MySQL, if you're on Postgres, and you are dealing with a system that is limited by a single writer, that is one of our primary use cases that we support, and that would be a good fit for TiDB. Secondly, database consolidation. If you have massive amounts of relational database instances or a combination of different database instances, and you want to reduce complexity, consolidating all of these different individual databases into a single database is something that TiDB does actually better than potentially every other database on the market. If you want to have an operational data layer with a single source of truth for your entire business, where you can process and query large volumes of fresh data with high throughput and low latency, that's also an excellent use case for TiDB. And then finally, NoSQL modernization. If you went to NoSQL because you needed to scale and you didn't have a choice at the time, we are a good, excellent alternative if you want to go back to the SQL space while also being able to scale to the degree that you need. Now, jumping into a few of our use cases here. So TiDB actually runs the control plane, the metadata storage for the control plane of Databricks. And we are responsible for the jobs, queries, and notebooks, and user and clusters for each individual customer of Databricks. And this is Databricks actually foundation on one of their most critical services. And before this, they actually used a cloud-managed MySQL on AWS, Azure, and GCP. And they encountered massive scalability issues under growth. It caused downtime, and due to the multi-cloud nature of these managed services, it introduced a lot of complexity into their architecture. But the result of migrating to TiDB is they achieved more than 10 times the QPS than a cloud-managed MySQL instance. They reduced database downtime, they improved SLAs, they had much lower average P99 and P99 latencies. They simplified their tech architecture by eliminating all these different individual databases. And they're also reduced cost significantly by having less hardware costs and maintenance burden by having it all consolidated into a single TiDB cluster. Pinterest also runs on TiDB, and Pinterest is a foundational ad service. Particularly their machine learning platform for user recommendations now runs on TiDB. And they were carrying a massive data footprint on HBase, which has became way too expensive, way too time consuming, and way too complex to manage. And it was much too slow to meet the growing needs of Pinterest, and it was too slow to meet user expectations. And some of the pain points here is there was a very, very high operational cost. There was massive complexity. It was also missing functionalities like secondary indexes and support for transactions. And frankly, they were spending time almost on a daily basis band-aiding this together. But if we're moving to TiDB, they achieved a 80% reduction in costs and a 3 to 5x increase in P99 latency, or reduction, excuse me. And they also were able to achieve after write consistency and simplified architecture through a unified system. Plaid also was encountering issues with scale, and they were on Aurora. Had a massive sharded Aurora instances. And with each of these individual shards potentially had resource utilizations under 10%, which needed to be pre-allocated just in case that portion of the shard ended up receiving a massive amounts of traffic unexpectedly. And this led to just massive costs for Plaid. And that's why they transitioned to TiDB to replace all these individual sharded Aurora instances with a single unified database. And this led to better reliability and a much, much lower cost of ownership. They also were able to reduce their data footprint, and now their resource utilization on their compute nodes is increased from 10% to 60%. And then finally, for our final case study is Catalyst. And Catalyst is a SaaS company, and they consolidate data from Salesforce, Zendesk, Jira, and other processing analytics to produce actionable insights for their customers. And before they moved to TiDB, they were on Postgres and Elasticsearch, and they encountered massive pain points around having a high data volume, low query performance. Elasticsearch doesn't allow them to do joins at all. DDL was hard, so they pretty much just didn't do it, and so the costs were astronomical. And that's when they migrated to TiDB with TiFlash to allow them to have a single plane of their data where they can do both transactional and analytical workloads on the same cluster. And TiDB also operates on anywhere you want it to. We can deploy self-managed, whether that be on-premise or on any public cloud or data center. We can also deploy, we also have our own dedicated managed offering that deploys on AWS and GCP. And we have a serverless offering, which is free up to a certain extent, and where you can pay by usage and scale down to 0 if you need to. And an added benefit actually about the serverless offering is you can do a pure analytical workload on it without having to pay for the transactional compute that you would have to pay for on cloud dedicated and self-managed.